तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we looked at termination conditions for linear programming problems, and we ended the lecture by considering a problem that had unrestricted variable. In the example that we had chosen, x1 was the unrestricted variable and x1 was written as x3 minus x4, and we solved the problem optimally. The simplex table is shown here. Now in our discussion, we said at the end that the optimal solution is x3 equal to 4, x6 equal to 6 with z equal to 16, but we also observe that x4, which is a non-basic variable, has a 0 Cj minus Zj at the optimum. So x4 tries to enter the basis, but when x4 enters the basis, we realize that we do not have a leaving variable. We get a feeling that we see unboundedness in this example. We might also feel that because a non-basic variable has Cj minus Zj equal to 0 at the optimum, it could indicate alternate optimum. Actually what is happening is it is indicating neither. The reason is, when we had substituted x1 equal to x3 minus x4, and in this example x3 equal to 4, this will be taken back to the original problem with variable x1 taking value 4 and z equal to 16. The original problem has a solution x1 equal to 4 and z equal to 16, but that is reflected as x3 equal to 4, x4 non-basic equal to 0. Now if x1 has to take a value 4 in the optimum solution, then one way of getting this 4 is 4 comma 0. For example, we could have a solution x3 equal to 5, x4 equal to 1 and x1 would still be 4. So that is being reflected by the presence of this 0 under x4, where x4 is trying to enter the basis. It is suggesting that we could have alternate combinations of x3 and x4, but the effective value for x1 will remain at 4. Also, because there are infinite ways of getting this 4, it could be, for example, 4 0 or 5 1 or 6 2 or anything, one gets a feeling that x4 can actually take any positive value and x3 can be correspondingly adjusted. Therefore, we get a feeling that we are going to have an unbounded solution. So this phenomenon will occur whenever we are working with a problem that has an unrestricted variable. If that variable has to be in the solution, then the variable being represented as a difference of two variables, one of them will be in the solution. In this case, this unrestricted variable takes a positive value, so this component will be in the solution with 4. The other one will be non-basic at 0, but it will try to enter the basis by having a 0 value for Cj minus Zj and will indicate something very similar to unboundedness. This is something which we will have to understand whenever we are solving a linear programming problem where the original problem has an unrestricted variable. Now, once again in the last lecture we looked at the various termination conditions, and let's have a quick recap of these before we move to the next topic. The various termination conditions were for unique optimum, alternate optimum, unboundedness, and infeasibility. We looked at these 4 termination conditions in the last lecture. Now, the alternate optimum is always represented by a non-basic variable having a Cj minus Zj equal to 0 at the optimum and trying to enter. Unboundedness will be indicated by having an entering variable, but unable to get a corresponding leaving variable, and infeasibility is indicated by the optimality condition being satisfied, but an artificial variable will be in the basis with a strictly positive value. We also said that if the artificial variable is in the basis with value 0, then it indicates that we are trying to solve a linearly dependent system of equations. Now, from all these termination conditions, we generalize and we state what is called the fundamental theorem of linear programming. The fundamental theorem of linear programming is as follows. Every linear programming problem is either feasible or unbounded or infeasible. If it has a feasible solution, then it has a basic feasible solution. If it has an optimal solution, then it is basic feasible. Now, this theorem is important for many reasons. All the termination conditions get reflected in the first sentence. So, every linear programming problem has to satisfy one of these 3. It will have an optimum, which could be a unique optimum or an alternate optimum. It could be unbounded or it could be infeasible. So, these are exactly the things that we looked at in the termination condition. If it has a feasible solution, then it has a basic feasible solution. It means that there is at least one counterpoint solution for this. This comes from the fact that the region that we look at, the feasible region in every linear programming problem, is a convex region. So, if the problem is not infeasible, then it is feasible. It means there is at least one counterpoint solution. And if it has an optimum solution, then the optimum solution has to be a counterpoint solution and it has to be a basic feasible solution. So, this theorem is important. We will come back to this theorem, refer to this theorem a little later when we look at some aspects of duality. So, in summary, the linear programming problem, we have so far looked at solving linear programming problems for maximization objective, minimization objective. We have looked at different types of constraints. We introduced slack variables, negative slack or artificial variables. We also understood that artificial variables are needed to get a starting basic feasible solution. We also looked at the various aspects of the simplex algorithm in terms of initialization, iteration, termination, and then we have defined the fundamental theorem of linear programming. We now move to a very important aspect of linear programming called duality. Now, let us explain duality by taking the same example that we looked at the beginning of this course. The problem is to maximize 6x1 plus 5x2 x1 plus x2 less than or equal to 5, 3x1 plus 2x2 less than or equal to 12, x1 x2 greater than or equal to 0. Now without solving this problem, let us try to get some estimates of the objective function. For example, if we did not have either of these constraints, if the problem did not have any constraint at all, then an obvious answer would be x1 equal to infinity, x2 equal to infinity, z will be infinity. And because we have these constraints, the z value at the optimum will have to be less than that infinity, or putting it differently, this infinity is a very easy simple upper bound to the value of the optimal solution. Now let us look at other ways of getting better and better upper bounds. For example, if we can look at this problem and confidently say that the z value at the optimum cannot be more than 1000, then 1000 becomes an upper bound to the objective function at the optimum. Now one of the simplest things to do is to multiply the second constraint by 3. If you multiply the second constraint by 3, we get 9x1 plus 6x2 is less than or equal to 36. We know that the optimum solution has to be feasible. Therefore, x1 and x2 are greater than or equal to 0, and the optimum solution has to satisfy all the constraints. So the optimum solution has to satisfy this constraint, 9x1 plus 6x2 is less than or equal to 36. So 9x1 plus 6x2 is less than or equal to 36. For x1 x2 greater than or equal to 0, 9x1 plus 6x2 is greater than 6x1 plus 5x2. Therefore 6x1 plus 5x2 should be less than or equal to 36. Therefore the optimum solution should have an objective function value less than 36. 36 is an upper bound to the objective function value at the optimum. So you could get z equal to 36. Now let us do another thing. Let us multiply the first constraint by 6. Now we get 6x1 plus 6x2 less than or equal to 30. Now by the same logic, x1 and x2 are greater than or equal to 0, 6x1 plus 6x2 is less than or equal to 30. Now 6x1 plus 5x2 is less than 6x1 plus 6x2, which in turn is less than 30. Therefore 30 is an upper bound to the value of the objective function at the optimum. Now we can go back and say this problem cannot have an objective function of more than 30 at the optimum. So we look at 30. Now let us look at a third. Now in some sense this 30 adds more value to us than this 36, because we are now zeroing on, we now realize that this problem cannot have an optimum objective function value of more than 30, it can be 30 or less. Now let us look at a third thing. Let us multiply this by 2 and add this. So this will become 3 into 2 6 plus 1 7x1, 2 into 2 4 plus 1 5x2 less than or equal to 29. 12 into 2 24 plus 5 29. Once again by the same logic, 7x1 plus 5x2 should be less than or equal to 29, 6x1 plus 5x2 is less than 7x1 plus 5x2, x1 x2 greater than or equal to 0, so 6x1 plus 5x2 is less than or equal to 7x1 plus 5x2, which in turn is less than or equal to 29. So 29 is another value of the upper bound. We are doing this in such a way that we are progressively reducing this upper bound value. Now what do we understand out of this, particularly this third? Now what we understand is this: if I multiply the first inequality say by an a1 and I multiply the second one by an a2 such that a1 a2 greater than or equal to 0, otherwise the sign of the inequality will change and so on, we maintain the a1 a2 greater than or equal to 0. And if we multiply this by an a1 and this by an a2 such that a1 a2 greater than or equal to 0, and in the resultant process we get 1 into a1, or in the process whatever we multiply, so we get if 1a1 plus 3a2 is greater than 6. For example, if the coefficient, I multiply this by a1 to get a1 x1 plus a2 x2 less than or equal to 5a1, 3a2x1 plus 2a2x2 less than or equal to 12a2, and then I add this, so I get a1 plus 3a2. So if a1 plus 3a2 is greater than or equal to 6 and a1 plus 2a2 is greater than or equal to 5, then 5a1 plus 12a2 will be an upper bound to the objective function value at the optimum. To repeat again, what we understood from this, here we multiplied this by 2 and this by 1. So in that example a1 was 1, a2 was 2. So you multiply the first inequality by a1, second one by a1, a2 greater than or equal to 0, such that 1a1 plus 3a2 is greater than or equal to 6, 1a1 plus 2a2 is greater than or equal to 5, then 5a1 plus 12a2 will be an upper bound to the objective function. Now why did we do all this? We want to find out what is the smallest value of the upper bound that we can get. Now to do that, what we need to do is to multiply this by a1 and a2 such that a1 plus 3a2, to find a1 and a2 such that a1 plus 3a2 greater than or equal to 6, a1 plus 2a2 greater than or equal to 5, then 5a1 plus 12a2 is an upper bound, and a2 greater than or equal to 0. Now if we are able to find out any a1 a2 which satisfies this and this, then we know that 5a1 plus 12a2 is an upper bound to the value of the objective function at the optimum. Now if we want to find out the minimum value that this upper bound will take, then obviously we try to find out a1 a2 such that this is minimized. So that a1 a2 which will satisfy all these conditions and will minimize 5a1 plus 12a2 will give the minimum possible value that this upper bound can take. Now this is another linear programming problem that has come out of the original problem. Now if we replace a1 by y1 and a2 by y2, you will get minimize 5y1 plus 12y2 such that y1 plus 3y2 greater than or equal to 6, y1 plus 2y2 greater than or equal to 5, y1 y2 greater than or equal to 0. Now this problem is called the dual of this problem. So if this problem is called the primal, the given problem is called the primal, this problem is called the dual of this problem. So the dual provides the minimum value that this upper bound can take, and dual is another linear programming problem which is written from the original one. Now what are some of the characteristics of the dual to begin with? Now every problem, primal problem has a dual. By this logic we can write a dual for every primal problem. We will take another example to write the dual and learn more about how to write the dual. But before that, what we need to do is this. This is a 2 variable 2 constraint problem, but what happens is if the primal is a maximization problem, then the dual is a minimization problem. The primal has 2 constraints, the dual will have 2 variables because these y1 and y2 represent the a1 and a2, and by definition these a1 and a2 come because there are 2 constraints. So the primal has 2 constraints, the dual has 2 variables y1 and y2. Now these 2 constraints come from the fact that these 2 variables are there in the primal, because each of these is written for these variables. So the dual will have as many constraints as the number of variables the primal will have, and it will have as many variables as the number of constraints the primal will have. Now the right hand side values of the primal will be the objective function values of the dual, and the right hand side values of the dual will be the objective function values of the primal. In a 2 by 2 example such as this, we may end up seeing For example, we may not be able to clearly understand the fact that two variables become two constraints there. Much later we will take a different example to show all these properties. In summary, the properties are, if the primal is a maximization problem, dual is a minimization problem. The dual will have as many constraints as the number of variables in the primal and as many variables as the number of constraints in the primal. The coefficient matrix of the primal will become a transpose here, it will get transposed and it will appear as it is. The right hand side values become the objective function coefficient values and the objective function coefficient become the right hand side values. Now we will keep this as the base primal dual relationship. We will assume that the primal is a maximization problem, and if the primal is a maximization problem with all less than or equal to constraints and all variables greater than or equal to 0, the way we have derived the dual, we know dual will be a minimization problem with all constraints greater than or equal to, all variables greater than or equal to, and having the additional properties in terms of number of variables becoming number of constraints becoming number of variables, coefficient matrix becoming the transpose, objective function becoming the right hand side and right hand side becoming the objective. Now let us go back to this. So whatever we had explained you can see again in this sheet. So these are the, for every y1 and 3y2 satisfying this, we get an upper estimate of z. So the lowest value it can take is given by another linear programming problem P2 that we have derived here. Minimize 5y1 plus 5y2, w equal to 5y1. It is customary to write the dual's objective function as w instead of z. Normally we use the vector x to represent the solution to the primal and z to represent the objective function value of the primal. We use y to represent the dual variables and w to represent the objective function value of the dual. So you have minimized w equal to 5y1 plus 12y2 and so on. Now if the primal is maximized z equal to cx subject to ax less than or equal to b, x greater than or equal to 0, the form that we have looked at. In this case c, b are vectors and x are vectors, a is the matrix. The dual will be minimized w equal to yb subject to a transpose y greater than or equal to c, y greater than or equal to 0, which are the things that we have seen right now. Right, now the next thing that we need to do is, if we are given a primal which satisfies exactly this, if we are given a primal which is a maximization problem with all less than or equal to constraints and all greater than or equal to variables, we assume now that we know to write the dual. The dual will be a minimization problem with all the properties that we have seen. But we are also aware that linear programming problems can have two types of objective functions, maximization or minimization. It could have three types of constraints, greater than or equal to an equation. It could have three types of variables, greater than or equal to, less than or equal to and unrestricted. So what will happen to the dual if we have something other than this? For example, if this is a minimization, if this is greater than or equal to, or this is an equation, or this is a less than or equal to, this is unrestricted. The other things will always be satisfied. What are the other things? The number of constraints equal to the number of variables equal to number of constraints, coefficient matrix becoming transpose, right hand side becoming objective function and objective function becoming right hand side. Those things will be there, they will not change. Only these inequalities, the sign of the constraints and the sign of the variables will change depending on what we have here. So we take an example and then write the dual for that example and then understand how for any given primal we can write the dual. Right now we can write the dual if the primal is a maximization problem with all less than or equal to and all greater than or equal to. Then we will learn how to write the dual whatever be the primal in terms of type of constraint and type of variable. So let us take the other example. The problem that we take is minimize (8x1) plus 5x2 plus 4x3 subject to 4x1 plus 2x2 plus 8x3 equal to 12, 7x1 plus 5x2 plus 6x3 greater than or equal to 9, 8x1 plus 5x2 plus 4x3 less than or equal to 10, 3x1 plus 7x2 plus 9x3 greater than or equal to 7, x1 greater than or equal to 0, x2 unrestricted and x3 less than or equal to 0. Now let us go back to this table. Now we realize that all possible types of objective functions, constraints and variables are covered in this example. It has a minimization. We have earlier taken a maximization problem. There are 4 constraints and 3 variables. So we would expect the dual to have 3 constraints and 4 variables. The constraints are equation, greater than or equal to, less than or equal to. All the 3 types are covered, as well as all the 3 types are covered. We have a greater than or equal to, unrestricted and less than or equal to. We will take you through the various steps using the PowerPoint slides. So we have written the same problem here once again. Now the first thing we need to do is, we assume that we know to write the dual if the primal is in the standard form that we are aware of. If the primal is a maximization problem and has all constraints less than or equal to and all variables greater than or equal to. So what we do now is, we convert this problem into the form that we know, which is a maximization problem with all less than or equal to and all greater than or equal to. For example, converting the objective function is not very difficult. You can multiply with a -1 and convert it into a maximization problem. This constraint is desirable because it has a less than or equal to. We need to do something about this, this and this. We also know, for example, that if you multiply this with a -1, it will become a less than or equal to. Similarly, this is desirable. This again we can multiply with minus or redefine the variable. Here we know how to convert, we make it a difference of 2 variables. So we will do all this and see how this problem transforms itself. Now first thing is, we know that variable x2 is unrestricted in sign. So we replace it as a difference of 2 variables, x2 equal to x4 minus x5. So this is in the correct, the required form, this is not, so this becomes x4 minus x5 and x3 is less than or equal to 0. So x3 is replaced by minus x6, where x6 is greater than or equal to 0. So first thing we do is, we make all these variables into the form which we are comfortable with, and then we go back and substitute both in the objective function as well as in the constraints. So when we do that, we get this. So x6 becomes greater than or equal to 0, but if you look at this, you have a minus coefficient, you have a minus 8x6 here instead of the plus 8x3, because this variable has been replaced by a minus x6. So you will see the change in all the 4 coefficients as well as in the objective function. If we look at the second variable, which was unrestricted, which is now replaced by x4 minus x5, so 5x2 becomes 5x4 minus 5x5. This 2x2 becomes 2x4 minus 2x5 and so on. Now because we have added another variable, we now have 4 variables. Original problem 3, we have now 4 variables and we have 4 constraints which are given from 3.6 to 3.9. So this problem is the same as the previous one, but with an additional variable. The next thing we do is, we convert the objective function into the form that we know. We want to bring it to a maximization, so multiply the objective function by -1 to get it into a maximization form. Now let us look at these 4. This is desirable, it is already a less than or equal to. this entire constraint can be multiplied with a minus 1 to make it less than or equal to. Here again we can multiply this with minus 1 and make it a less than or equal to. Now what do we do for the equation? The equation we write it as two constraints. One is 4x1 plus 2x2 plus 8x3 greater than or equal to 12, 4x1 plus 2x2 plus 8x3 less than or equal to 12. So the equation is written as two constraints, one of which is a less than or equal to straight away. The other one, which is a greater than or equal to, is now made a less than or equal to by multiplying with a minus 1. So if we do that, therefore your 4 constraints would now become 5, as you can see here. Now you realize that all the constraints have been converted into the less than or equal to form. The 10 remains as 10, this greater than or equal to 7 has become less than or equal to minus 7, the greater than or equal to 9 has become less than or equal to minus 9. The equation has become two constraints, one less than or equal to and one greater than or equal to. So the original problem had 3 variables or three variables and 4 constraints. Now the transformed problem has 4 variables and 5 constraints. Now we have brought this to the form we are comfortable with. Remember, this is still the primal, this is not the dual. We have to write the dual for this problem. The only reason we did this is because we know to write the dual for this problem. So we have brought it in the form we are comfortable with, and now we are going to write the dual for this. So the dual will now be a minimization problem. So dual will take the form minimize, go back to the previous slide. It will become minimize. Now we will introduce 5 variables corresponding to the 5 constraints. We will call them y1, y2, y3, y4 and y5. y1, y2, y3, y4 and y5 corresponding to these 5 constraints, and the dual will have 4 constraints, one for each variable. It will be a minimization problem because this problem is a maximization problem. So we now get the dual, which is minimize 12y1 minus 12y2 minus 9y3 plus 10y4 minus 7y5, subject to these 4 dual constraints corresponding to the 4 primal variables, and all these 5 are greater than or equal to 0. Now this is in the form that we know, because we have written the dual for what has been transformed into a maximization problem with all less than or equal to constraints and all greater than or equal to variables. So it will become a minimization problem with all greater than or equal to constraints and all less than or equal, or all greater than or equal to variables. Now this dual has 4 constraints corresponding to the 4 variables in the transformed problem and 5 variables corresponding to the 4 constraints in the transformed problem. But the original problem has only 3 variables, so the dual should have only 3 constraints. The original problem has 4 constraints, the dual should have only 4 variables. So we will try to convert this problem once again such that we are able to get the other properties satisfied. For example, the dual to this problem should be of the form sum 12y1 plus 9y2 plus 10y3 plus 7y4, where y1, y2, y3, y4 are suitably defined dual variables. The dual to this problem should have 3 constraints with right hand side values 8, 5 and 4, and the sign of the constraint could be anything. The dual for this problem should have a coefficient matrix which is a transpose of this matrix. So we now bring this problem again into a form where those things are satisfied. And how do we do that? Now let us look at, let's go back to the previous one. Yeah. So this is the dual that we have written. We now need to bring this back into this form that we are comfortable with. So let's go back to the next one. Now first thing we do is this. Now look at all the 4 constraints. You now realize there is a 4y1 minus 4y2, 2y1 minus 2y2, minus 2y1 plus 2y2, minus 8y1 plus 8y2, minus 12y1 plus 12y2 in the objective function. So we can now replace y2 minus y1 as a new variable y6. We can do that, and therefore we reduce the number of variables. Now 5 variables will become 4. Remember again, this problem had 4 constraints and we would want the dual to have 4 variables. So we do that and we get we get this, we get 12y6 plus 9y3 minus 10y4 plus 7y5 subject to these, and we have y3, y4, y5 greater than or equal to 0. y6 is unrestricted in sign because y6 has been defined as a difference of two variables. So we get one unrestricted variable. Now one more thing that we can observe is there is this y4 which keeps coming here, minus 10y4 in the objective function. That we want the final objective function to be of the form 12 into 12y1 plus 9y2 plus 10y3 plus 7y4, where y1, y2, y3, y4 are suitably defined variables. This 10y4 alone has a minus sign, so we replace y4 with a minus y7 and write y7 less than or equal to 0. So this will become plus 10y7 in the objective function, and the coefficients there will change. Now this becomes, now you realize that we have made the objective function in tune with what we want. We have got this 12, 9, 10 and 7, we have got this 12, 9, 10 and 7 here. Now subject to, we have made those changes also in the y4, now all these have been converted to y7. Now we have taken care of the variables. Now we realize that the 5 variables that we had are now become 4, one of them has become unrestricted, other has become less than or equal to type, 2 of them remain as greater than or equal to type. Now we go back and try to adjust the constraints. The original problem has 3 variables, so dual should have 3 constraints. Now multiplying constraints 3.14 and 3.15 by minus 1 and writing the modified as an equation, you will see that writing the modified constraint 3.15. Now 3.15 and 3.16, if we look at it very carefully, if we multiply 3.15 with a minus 1, we would get 2y6 plus 5y3 plus 5y7 plus 7y5 less than or equal to 5. The third constraint is 2y6 plus 5y3 plus 5y7 plus 7y5 greater than or equal to 5. So together they will become an equation. So we will reduce one constraint by 1. And then we go back to the other one, to the previous slide. You look at the first constraint has all coefficients negative including the right hand side. So we can multiply the first constraint with a minus 1, convert the inequality to a less than or equal to type and make the right hand side plus 8. If we do that, we get this, we get now 12y6 plus 9y3 plus 10y7 plus 7y5 subject to these. Now we can, since y6, y3, y7, y5 are very generic variable names, you can rewrite them as y1, y2, y3, y4 and replace this. Now if we keep this and compare with this problem, let us just write only the dual here, maximize 12y6. In fact, let me use the term y1, y2, y3, y4 now, which means variable y6 has become variable y1 here, plus 9y2 plus 10y3 plus 7y4 subject to 4y1 plus 7y2 plus 8y3 plus 3y4 less than or equal to 8, 2y1 plus 5y2 plus 5y3 plus 7y4 equal to 5, 8y1 plus 6y2 plus 4y3 plus 9y4 greater than or equal to 4, y1 unrestricted, third variable, so y3 less than or equal to 0, y2, y4 greater than or equal to 0. The third variable was y7 which is less than or equal to 0, third variable is y3 which is less than or equal to 0. So now this is the dual corresponding to this primal. Now we can do two things. Now we know to write the dual to any given primal. any given primal we can convert any given primal into a standard form. The standard form that we know is a maximization problem with all less than or equal to constraints and all greater than or equal to variables. Now for that problem we can write the dual, which will be a minimization problem with all greater than or equal to constraints, with all greater than or equal to variables, number of constraints equal to number of variables in the dual equal to number of constraints in the primal, coefficient matrix becomes transpose and so on, and then we adjust the written dual in such a way that we bring it back having all the properties where the number of constraints is equal to the number of variables is equal to number of constraints, objective function becomes right hand side becomes objective function, transpose and so on. We will then realize that depending, only places where we aren't sure because what happens if this is an equation? How will this equation get reflected in the dual? How is this getting reflected in the dual? How are these four types, the equation greater than equal to, less than equal to, get reflected in the dual? Similarly, how are these things getting reflected in the dual? Rest of the things we know. Because we know all these three numbers are going to come here. So one is to go back, convert it into the form that we know, write the dual and convert the dual back into the form where these properties are satisfied. The other is also to try and understand what exactly happened here. Now let us look at this. The first constraint is an equation. The first variable is an unrestricted variable. The second variable is an unrestricted variable. The second constraint is an equation. So there is a relationship between the unrestricted variable and the equation, and that happens because the unrestricted variable in the original case now gets split into two variables. Now these two variables become two constraints which later get converted into an equation. So there is a relationship between the unrestricted variable and the equation. So if a primal constraint is an equation, then the dual variable will be unrestricted in sign. That is an easier thing to do. The rest of the things are a little not so easy as to understand here. Now for example, this is a minimization problem. In the minimization problem, this constraint is a greater than or equal to constraint. The second constraint is a greater than or equal to constraint. Now there are many ways of understanding this relationship, and let me propose one way which I often use to do that. In all linear programming problems, if the problem has a maximization objective, then it is desirable to have a constraint of the less than or equal to type. If the problem has a minimization objective, it is always desirable to have a greater than or equal to type constraint. And in all linear programming problems, a greater than or equal to type variable is always desirable. A less than or equal to type variable is undesirable. So if we follow this guideline and go back and understand, this is a minimization problem. So this is a desirable kind of a constraint. So the corresponding variable will be a desirable kind of a variable, greater than or equal to. For a minimization problem, this is an undesirable kind of a constraint. This is not the constraint you would like to see in a minimization problem normally. So I would call it an undesirable kind of a constraint. So the third constraint is of the undesirable type. The third variable y3 will be an undesirable variable, which is a less than or equal to. There is more than one way to understand this relationship, but over a period of time I have found it convenient to interpret it this way. Now this is a desirable kind of a constraint. The fourth variable y4 is a desirable kind of a variable. Now let us go back to the variables. This is a desirable kind of a variable. So the first variable is a desirable kind of variable. Now go back to the first constraint. For a maximization problem, you will get a less than or equal to, which is a desirable type. This is an undesirable kind of a variable. So for a maximization problem, the third constraint will be the undesirable type. So over a period of time, you can use this, or you can remember it in a different way. If a minimization problem has a greater than or equal to, then corresponding maximization problem will have a greater than or equal to, and so on. So there are different ways of remembering this. So to write the dual, one could take all the labor and time to convert this into the standard form that we know, and then write the dual to the standard problem, and then convert it back into the form that we are comfortable with, or we could go back and then remember these things as we write. So we create a table which would help us understand the primal dual relationships, and the table is like this. So we now call the primal as a maximization problem and the dual as minimization problem. 1. Number of constraints equal to number of variables. 2. Number of variables become number of constraints. Right hand side become objective function. Objective function becomes right hand side. Coefficient matrix A becomes A transpose. Now the next easier things are equation becomes unrestricted variable. Unrestricted variable becomes equation. Then comes maximization problem. The desired type of constraint less than or equal to constraint will become a greater than or equal to variable, because greater than or equal to is always a desired variable no matter what the objective function is. Maximization problem, greater than or equal to constraint is not the desirable one. So this will convert itself into a less than or equal to variable. Greater than or equal to variable is always a desirable one. So for a minimization problem, this will become greater than or equal to constraint, and 11 less than or equal to variable will become less than or equal to constraint. So one can remember this table also. Now one can do another thing. Suppose this was the primal, we had called this as 12x1 plus 9x2 plus 10x3 plus 7x4 and so on. If this were the primal, then what will be the dual? This will automatically become the dual. In fact, whatever is applicable from this to this is also applicable from this to this. Now anything can be the primal, the other will be the dual. For example, if this is the primal, primal maximization, dual minimization. Primal first constraint less than or equal to, maximization first constraint less than or equal to, first variable of the dual will be greater than or equal to, you find the greater than or equal to here. So like this you can interpret, keeping this as the primal and this as the dual. We can go back and shift the same thing. If this is the primal, the only thing we need to do now is primal becomes minimization problem. This is primal, this is dual. Now you can go back. Now if this is the primal, minimization is the primal, second constraint is greater than or equal to, so second constraint is the correct type of constraint, the dual is maximization. So for a minimization problem, a greater than or equal to constraint will give greater than or equal to variable. So second constraint is this type, so second variable is this type. So one need not always restrict oneself to saying this will be the primal and that will be the dual and so on. Any one of the problem can be the primal, the other problem will automatically become the dual. So this table would help us write the dual for any given primal. So, in summary, what we have seen in this lecture is we have introduced the problem of the dual, and we have also tried to explain that the dual is inherent, it comes out of the primal naturally and it is inherent or hidden in the primal, and we have also learnt how to write the dual for any given primal linear programming problem. In the next lecture we will see more of the primal dual relationships.